We were talking about pumping a parse tree. Let me just refresh our memory. If you have a parse tree that looks something like, let's say, how about this? This is a parse tree for some grammar. I don't really care what the grammar is. If you have such a parse tree, in this particular example, the string that is generated is AACBB. So AACBB is in the language that's generated by this grammar, whatever it is. I don't care what the grammar is. I just want to talk about this parse tree. You can pump the parse tree whenever you see a non-terminal symbol on the inside of the tree, which is a descendant of itself. And in this case, I see an S, which is a descendant of another S. I have this S, and its descendant is another S. Or actually, I also see the top S has an S as its descendant. So there's more than one way you can do this, but I'm going to pump this part of the tree. What that means is, I'm going to write this top part the same like it is. Pumping the parse tree means you replace the whole smaller like descendant, which is here in the blue. I replace the blue with the entire thing that you saw in the red in the beginning. So this S now is going to do this again. All right. What used to say just S goes to C from before, I have replaced with this entire part right here, which I will again circle as blue. All right. And the string that you get from this parse tree is now AAACBBB, and that apparently is also in L. All right. And I could continue doing this pumping over and over again. So this is called, what did I do there? I pumped the S. Now, in particular, I pumped this S right there. All right. By replacing the one below with all the descendants from the one above. All right. That's called pumping the parse tree, or pumping this part of the parse tree at least. All right. And in this example, we started with a squared c b squared in L, and we were able to demonstrate that that actually means that a cubed c b cubed is in L. And if we continue doing the pumping, you can do this as many times as you like. We could pump again and again, right? To show actually in this example that a to the n, c, b to the n is in L. For all n at least bigger than or equal to 2, right? 2 was the one we started with. Any one greater than that, all of those also must be in L. All right. This is the idea behind pumping parse tree. Anybody got any questions about that? All this we said last time. I'm just trying to get us back up to speed. All right. Now, yeah.
Yeah. So couldn't you tell me to do any parse tree? Like, is there like a special
Yes.
rule you have to follow?
Yeah. Actually, this is a great question, and this is what I was about to discuss. When is this possible to do? And the answer is basically, well, you can do it whenever you want. Only, so one thing that is required is you actually need, oh, my iTunes is bouncing. You actually need one of the non-terminals to appear below itself in the parse tree. If you had something like just, S goes to X, Y, and then X goes to A, Y goes to B, you can't do any pumping here, because pumping requires replacing the lower occurrence of the same thing by one of the upper occurrences of the same thing. So we must have a non-terminal as its own descendant. But otherwise, that's it, right? Whenever you have that scenario, you can pump it. We must have a non-terminal as its own descendant. Ant, right? It ends with an A. Okay? In general, what this looks like is, so I was using like sort of a specific, is there another question? No, I heard something. All right. Generally, it looks like this. So I was using like a specific made up example there, but in general, the scenario that you have is you have some, of course we always begin with S on the top. And then if you have, I'm going to draw sort of a schematic here. That squiggly means that's not necessarily just one thing, but I'm just trying to indicate there may be all kinds of other stuff happening in the tree, but there's part of the tree in which the A is below the S. And then you have another A sitting below that A. Again, it doesn't have to be immediately below, it just has to be somewhere below it. And then this A turns into some string at the end, say W. And this is the scenario in which you can do the pumping. Now, in such a tree, you are also, like, W is not going to be the only part of the string at the end. Each part of this tree is also going to produce other parts of the string. So I'm going to try and indicate that like this. Oops. I'm going to write U, V, W, X, Y here. So I'm trying to indicate the entire string at the bottom here. The U comes from like the stuff on the left side of the original S that wasn't part of the A part. And then that A part on its two sides, it generates some other stuff, which eventually become the strings V and X on the two sides of the A. And you still get the W in the middle. All right. So generally, a parse tree looks something like this. And then if it looks like that, we pump it, and it becomes the same kind of thing, but it's going to have sort of an extra A in it, right? And then what does the string look like at the end? Well, the two sides of the S, they still generate U and Y, right? Because I'm not modifying that part of the parse tree. The upper A also is not modified, so this also still generates V and X. But now the lower A is also generating V and X, right? And so here we get the string now is U, V squared, W, X squared, Y, right? Yes? Yeah, sorry. X on the right side there. Yeah, thanks. A, the big A makes a V on the left side and an X on the right side. Right there. Thank you for that. All right. This is the general scenario, what it looks like when we do the pumping. Sorry, I got to stop this bouncing iTunes. I don't know what's... Yeah, all right. I'll update my iPad. Okay. Great. Now, this, I will remind you, this is only possible to do when A appears as its own descendant. I will also say, this is only interesting if V and X are not both the empty string, all right? If V and X were both the empty string and you did this pumping, then the string you get after the pumping would be the same as the string you got that you already had. So the pumping really would have no effect. If the V and the X are both the empty string, pumping the parse tree doesn't do anything. It's still legal, but it has no real relevance. All right. This is only interesting if the V and the X are not both epsilon. Another way of saying this, and you'll see this language is going to be used in a few minutes. I will say, i.e., I want to say this, the terminal string generated by the upper A, which in this case is VWX, sorry, A, I mean the upper capital A, which in my example is VWX, right, is longer than the terminal string generated by the lower A, which in this case is just W. longer than the terminal string generated by the lower a, which in this picture is just the w, right? This is the same as saying that v and x are not both the empty string. I'm saying the string you get from the a above, it's actually different, and it must be longer, it can't be shorter. It's actually longer than the string you get from the a below, all right? If this, what I just wrote, is satisfied, that's the only interesting case, and in that case, it has a name. This is called a pumping parse tree. So that the definition is basically what I just wrote. I'm going to write it again. A pumping parse tree is a parse tree for a particular string. It's a parse tree in which two things are satisfied. First of all, I'll just say it out loud first. First of all, there is a non-terminal which appears as its own descendant. Also, the string that's generated by the one above is longer than the one that's generated by the one below. That's what I'm going to write. So I'm going to say there is a parse tree in which some non-terminal, I'll call it A, appears as its own descendant. And second of all, the string generated by the upper one is longer than the string generated by the lower one. The non-terminal string, the terminal string, not non-terminal, like the one you get at the bottom, the terminal string generated by the upper A is longer than that generated by the lower one. All right. If those two properties are satisfied, it's called a pumping parse tree. So all the specific examples that I've written down so far, those were pumping parse trees. One non-terminal sits as a descendant of another, and the string generated by the one above is longer than the string generated by the one below. So for example, this right here, this guy is a pumping parse tree because a S sits below another S, and if you look at the strings that they generate, like in this case, these two S's, the one above generates ACB, but the one below only generates C. So the one above generates something that's longer. Versus, say, this one here, this is not a pumping parse tree because nothing is its own descendant. All right? Great. Pumping parse tree. And the big theorem, all of this is leading to some way that we can tell if a language is context-free or not. All right? Specifically, to show that it is not a context-free. There's a big theorem about context-free languages. I'm going to say if L is context-free, this is a technicality here. If L is an infinite context-free language, basically every language we ever talk about in this class is infinite, meaning it has infinitely many strings as part of the language. If it has only finitely many strings as part of the language, then it's automatically a regular language, and basically you don't have very much interesting to say about it. But if L is an infinite context-free language, then there is some string with a pumping parse tree. All right? That is to say, no matter what the language is, as long as it's context-free, it is possible to find some string that has a parse tree which has these properties. That is, one non-terminal sits below itself, and the strings that the upper one generates are longer than the strings that the lower ones generate. I want to try to just talk about why this is true. We'll do a little proof. There's not much to this. just to see why this is a property of context-free languages. So first of all, remember, you can only really talk about parse trees if it's a context-free. So if it's not context-free, then you can't even discuss a parse tree at all, because there can be weird non-context-free grammar steps mess up the parse tree structure. But why is it that every context-free language must have a pumping parse tree? That's what I want to talk about. I have to explain why. Every language has a string which requires you to write a parse tree for that string, which has the thing about one descendant of itself, that business, all right? First of all, every string has a smallest parse tree, right? It is actually possible to have a string with more than one different way to write a parse tree for it, but if there are more than one way, one of them must be the smallest. There may not be a largest, but there must be a smallest parse tree for any given string. If you've checked out the homework, you see there's some question about several different parse trees for the same string. But anyway, there always has to be a smallest parse tree for the same for every string. But L has infinitely many strings. Infinitely many strings, right, in it. That's just part of the assumption. I said if L is an infinite context-free language. So every string has the smallest parse tree, but L has infinitely many strings in it. What that means is there are some strings which require very, very big parse trees, right? It's not like every string in the language cannot have require only a small parse tree, because they're only sorry, I left an ingredient out, not from the theorem, but also, let me just say, the grammar for L, this is the important thing that I didn't say. The grammar for L has only finitely many non-terminal symbols in it. Finitely many. The grammar for L only has finitely many non-terminals. That's like the big S, the big X, the big Y, right? What that means is, since your language is infinite, there must be some like really long strings, and those really long strings are going to require really big parse trees. And in particular, since there's only finitely many X's and Y's or whatever, a really big parse tree must require that there's some non-terminal that appears underneath itself, because there's only finitely many non-terminals, and you're going to have to start repeating them after a while, all right? So the grammar for L has only finitely many non-terminal symbols. That means some strings will require repetition of the symbols. Some strings will require repetition of the non-terminals. So we will get some strings, they may be really big ones. We will get some strings with, say, A above A, right? Because there's only finitely many choices for the non-terminals, but there's infinitely many possible strings. And so something's got to give there, and they're going to have to start repeating them, some of them, all right? So we will get some strings with an A above an A, all right? And I'm going to say we will get some strings with an A above an A, even in their smallest parse tree. What I mean is, there are going to be some strings where even if you write the smallest possible parse tree for that string, it still has an A above itself, all right? Now, how do we know that the string generated by the one above is bigger than the one below, all right? This is also part of being a pumping parse tree. It has the A above a A, or A inside a A or something. And also, the string you get from the one above is bigger than the string you get from the one below. Check it out. In a smallest parse tree, we'd have something like, you know, A up here, and then it makes above another A. This is like that picture I drew before. And let's say it makes the X and the Y here, all right? We must argue that X and Y are not both the empty string, right? That was the other part of what it means to be a pumping parse tree. So can I just say, I want to show X and Y not both the empty string. All right? Well, this is simple. If you assume just very briefly for a contradiction, if X and Y are both the empty string, then this looks like A, W, right? Like there is no X and Y. They're just nothing, all right? If the X and Y are both the empty string. But then this won't be the smallest parse tree. Since in that case we could have just done one A, right? There's no need to do the upper one and the lower one because those two things in the end don't have any effect. Since you could instead use just A down to W. You could like unpump it, you get the same string, all right? This is the contradiction, all right? Since that, I assumed that it was going to be the smallest, but if it is the smallest, then the X and Y, they can't both be the empty string, all right? If they were both the empty string, then it wouldn't be the smallest. This is the end of this little proof, all right? I hope you can hold this idea in your mind all at once, right? Since there's infinitely many strings, but only finitely many like choices for that A, some of them are going to have to repeat the A, even in their smallest possible representation. But if it is the smallest possible representation, then the X and Y, they cannot both be the empty string. Because if they were, then it wouldn't be the smallest representation. All right? This is the end of the proof of the theorem. This theorem I don't think really has a name. It's just a theorem about every context-free language has a pumping parse tree. Okay? And this is how we will show that a language is not context-free. This is how we can show some language L is not context-free. All right, the idea is you always do this sort of by contradiction. I mean, I suppose you could call this the pumping lemma for context-free languages. Every context-free language has our book says PPT, pumping parse tree. That's what I just demonstrated. I said that doesn't have a name. I think actually this is called the pumping lemma for context-free languages. I don't really care about that. That language I use just sort of for the general method by which we do all of this. Every context-free language has a pumping parse tree. To show something is not context-free, you can do it using this to get a contradiction. So here's an example. I want to do one, and then I want you guys to try some. This is everybody's favorite example of a non-context-free language. This is not context-free. This is like the example that should immediately come to your mind when I invite you to consider some non-context-free. A non-regular language, the standard example is A to the n, B to the n. Non-context-free, the standard example is A to the n, B to the n, C to the n. All right? This is not a context-free language. So I have to do like a little proof here. This is vaguely like showing something's not a regular language. The method is totally different, but you do have to write a little proof, although the proof is basically going to read the same in all different languages. You just have to tweak the details a little bit. So my proof is, I'm going to say, for the sake of a contradiction, that's those words, FSOC is what I write. For the sake of a contradiction, that means I'm making this assumption. In order to derive a contradiction, I assume L is context-free language. Then that means it has a pumping parse tree. for some string, and the string I'm always going to write in this same way that we have been writing those sort of diagrams. We assume that it does have a pumping parse tree for some string of this format, u, v, w, x, y, which is in L. And the point of that is you can pump the thing over and over again, and it means that u, v to the I, w, x to the I, y is in L for all I. Well, let me just say for all I. Let's say for all I natural numbers. All right? Remember, this comes from these diagrams like this, right? Your original pumping parse tree generates this string, u, v, w, x, y, and every time you pump it, it sort of gives you another v and another x. So you get u, v squared, w, x squared, y. That's if you pump it only once, but you can pump it as many times as you like and get any powers on the v and any powers on the x. All right. All right, now, this actually is sort of by rote. Like every single example you ever do, you're going to write exactly those words at the beginning. Now you have to consider the language in particular in this example. Look at the language in this example. We will automatically have this u, v, w, x, y is in L. So that means that u, v, w, x, y is of this format, a to the k, b to the k, c to the k, right? For some k. That's because that's what the language is. And also u, v, now this thing that I wrote here is true for all I, but in basically every example we're going to do, all that matters is if you just pump it once. So if we only pump it once, it is also true that u, v squared, w, x squared, y has the same format, I'll just say. It also looks like a to some power, not the same power, not the same k again, but it also looks like some bunch of a's followed by the same number of b's followed by the same number of c's, okay? This, in fact, is a contradiction. Does anybody, like, look at these two sentences here? Anybody feel like this is somehow contradictory? Anybody want to try and explain what's the problem with this? It involves identifying these pieces, u, v, w, x, y. They have to fit into this format somehow. Maybe the u is all a's and the v is also all a's, but then the w is all b's. Or maybe there's some mixture in there. Anybody have any ideas about this? I don't know. Maybe this doesn't look impossible. I'm gonna concentrate just on the v and the x because those are the ones that sort of change when I you want to think of it as when I move from this string to this string, the v's and the x their powers increase. Here's one thing I would say. The v, check out the v here. This might work if the v was like all a's or all b's. This definitely will not work if the v has a mixture of a's and b's. Because here you need all the a's to be before all the b's. But if v was something like ab, then when I square it, it would become ab, and then I have an a after a b, and that's not allowed. All right. So first thing I'll say is the v, and in fact the x also, but the v and x must. I'll just say this about the v. The same is true of the x, but it doesn't matter. The v must use only one letter. I mean, only all A's or all B's. When I say only one letter, that's not exactly what I mean. But the V must. I'll just write like I said. Must be all A's or all B's or all C's That's because if there were some mixture, since if V has a mixture, then U V squared W X squared Y won't have the right format, right? Because if V is something like ABB, then V squared would be ABB, ABB, and that's not allowed in the format of my strings in this language because we need all the B's to be after all the A's, all right? Okay, so maybe, I hope everybody agrees with that, right? So maybe V is all A's, or maybe it's all B's, or maybe it's all C's, right? So V is using all the same letter, and similarly with X, right? V is using all the same letter. X is also got to use the same letter for the same reasons. Now, they may not be the same as each other, but maybe the V is all A's and the X is all C's, or maybe it lines up in a different way. Maybe the V is all B's and the X is also all B's, right? Those are options. But anyway, now if we change, so changing from UVWXY to UV squared WX squared Y, how will the various numbers of A's, B's, and C's change? Any thoughts about that?
Either two of the letters that you have will double each time, it looks like, or they'll increase where one will decrease at the same rate, so they can't possibly be the same.
Yeah, that's right. Remember, both of these things are supposed to look like A to the K, B to the K, C to the K. The same amount of A's, B's, and C's. But what happens when you change from here to here? When you change from this string to this string? Well, maybe the A's and the C's will double, but not all three of them, right? Not the A's and the B's and the C's. Only two of them, their amounts will change, not all three. All right, then that's the point. So changing from this string to this string increases two of the letters. And it's supposed to look like A to the K, B to the K, C to the K. This will increase two, but not all three of them. And this is where our contradiction is. So that means that U V squared W X squared Y cannot be in L, because L requires all three of those exponents to be the same. And when we change from one word to the next, here they are all the same, but then to get to this one, we increase two of them, but not the third one. And that's what messes it up. All right, so this is not in the L anymore, and this is our contradiction. Because the whole point of the parse tree is the point of the pumping is that thing with the squares in it, it should also be in the L. But it ain't. Right? This is showing that something is not a context tree. I'm trying to put it all on the screen at once. It recedes as you get to the top. All right? Are there any questions about that one? It's a little tricky. Let's do one more, and then I have one for you all to try. When you write these little proofs out, they all kind of look the same, which is good. There are only certain little parts at which you have to think about what you're saying. Anyway, let's try. How about A to the N, B to the N plus 2, C to the 2N? This is not context-free language, all right? I'm going to say almost all the same stuff. So, I have to make like a little proof here. I'm going to begin with, for the sake of contradiction, assume it is context-free. So we have a pumping parse tree for some string u, v, w, x, y, which has to equal a to the k, b to the k plus 2, c to the 2k. And also u, v squared, w, x squared, y has the same form. Maybe I'll write it out. A to the n, b to the n plus 2, c to the 2n, where n and k might be different, all right? This is a somewhat condensed version of all the same stuff that I wrote in the first example we did. It has a pumping parse tree for some big string, and you have to write it out, u, v, w, x, y. It looks overly complicated, but this is as simple as it gets, unfortunately. All right? And again, you can say more or less the same stuff. Because of the order in which these things must appear, A's followed by B's followed by C's, it means the V and the X are not allowed to have a mixture of letters in them. If they start off with all the A's followed by all the B's followed by all the C's, and after you square them, they still have that same ordering, the V's and the X's may not have a mixture of the letters in them. So I'll say to maintain the format, really this has nothing to do with exactly what the exponents are, but just to maintain this kind of format, all the A's followed by all the B's followed by all the C's, the X and the V and the X cannot contain mixtures of the letters. The V and the X cannot contain mixtures of the letters. All right? They can't. And that means so when we go from one to the other, when we go from A u, v, w, x, y to u, v squared, w, x squared, y, we increase the number of two letters, but not all three. This is usually what your reasoning will be in this kind of proof. We are increasing the number of two of the letters, but not all three of them. And thus, u, v squared, w, x squared, y cannot be in L. That's because one of these exponents, like when you compare these two formats here, we only change two of the exponents, but not all three. And so one of them is actually the same, and that's not allowed. If they're going to have this format where the k is the same value of the all three, if you're going to change two of them, you better change all three of them, right? And that's the end. Any thoughts about that one? All right, great. I had some more complicated ones and some that I want you to try, but we got 10 minutes left. Would you mind if I just cut it off there, and then we will do some more examples of these next time? All right, great. Nobody minds. I will see you all tomorrow then, and we do have our homework due tomorrow as usual. Tomorrow will be the last time we talk about context-free. Then we'll go on to our next category of languages. See you all then. Yes.
I just have a quick question on the homework.
Sure. Yeah.
So I know we talked about it briefly in class, like the union between two languages like that. So
Yeah, you do that.
You do, okay. So it doesn't like you don't have to say like or like BC or CB because like I know this could mean like this or this, but could it also mean like or both or no? It can't. It just
Well,
means
both. So both means. Actually, in this case, there is no string which is in both sets, right? Because this set, they all have to look like this.
Oh, okay.
And this set, they all look like that, and there is no string that looks like that.
Okay, I follow. So this would be set up correctly then?
Yeah, and even like this, even in such a case,
Mhm.
this both. If
Would
there was a
satisfy
string
one
in
or the
both,
other.
then that would mean you could make it using the B, or you could make it using the C.
Gotcha.
So it would be the same. I
Okay.
think what you're wondering about is, should you also include the? I mean, should you also try like this, maybe?
Yeah, that's what I was
But
wondering.
these don't represent both. This
Right.
would be a string which looks like one of those followed immediately by one of those.
Gotcha. Okay.
But that's not. It would be something like that.
Right.
But this actually is not part of the union.
Okay.
Right? It's not in one or the other.
Right. Okay, that makes sense.
Yeah. So what you have is perfect.
Great. All right. Thank you.
Mm-hmm.